All right. So I will talk about basic sound processing, but don't treat it as a basic sound processing. I'll tell you some maybe story, and then I'll go from generics to specifics. And first, I'd like to explain all the words in this sentence, right? So, like, what the hell basic is, and the basic means that. I basically had no idea about sound processing before this, right? So, and yeah, these are my findings. So, and why the sound processing? I had some sort of personal traits. So there are some problems that I find interesting, and they somewhat stick in my head, and then they live there for ages, like for years. And the only thing that I could do with them is just try to implement something and get rid of it, right? So it's like, yeah, don't do web development, for example. Nice idea, right? Or write something meaningful in Common Lisp. So yeah, you see, it's very wide spectrum of topics, from like do robots to automatically count jumps through jump rope, and of course you take the most important part. No, you don't. Right, you take the one that bothers you every day. So I was doing some exercises with jumping rope, and I thought like, oh no, it's like too tough to count it by myself. So I need to do something about it, right? So it will be about this, yeah. This is how I thought about it, right? So I jump, thing records, then magic happens. You get spikes, you count them, and what profit. That's what you do, right? And then I recorded a small sample, and I thought, like, okay, this looks a bit different, right? So probably there is something else in this topic. So I started to dig into this, and and I thought that it would be much more entertaining to do it in Common Lisp, and it turned out to be much more entertaining than I thought. Yeah. So here's the spectrum of questions that you ask yourself when you start with this problem, right? You're like, okay, how the hell I record the sound? Or like, okay, maybe I don't want to record the sound. Maybe I want to just flow the file, right, and just analyze it. And what does the process sound mean, actually? And once you process the sound somehow, you need to be able to troubleshoot it, right? So you have some magic algorithm that does counting, but well, maybe you don't do it right from the first time this happens, right? And then maybe you want to play sound back because maybe you just loaded garbage, right? That is not sound at all, or like your library is broken, and then you might want to draw some fancy graphs like this one. Right, just to understand what the shape of the wave or things like this, and then at the very end you want to show the results. So I was in the top left corner, and I wanted to go to the bottom right, and the road was mostly like this. So the project is on the GitHub, and the is right out there, like with the whole drama when I tried to do stuff and it did not really work. Yeah, so what I thought that it would make sense not to jump every time that I want to test the algorithm, right? So, in this case,
very good for you.
Yeah, it should be, but it's like too tough. And when I do my hobby coding, I do it mostly at night, and yeah, it's
very bad for the neighbors.
Yeah, not that handy. So I thought that my magic algorithm should be able to work with many inputs, right? You should be able to get the data from the microphone, or you should get data from the file and process it. In the best case is that it should be the same thing, right? So that you don't change the code, and then you do some output. So here starts the magic of Common Lisp, because most of the libraries that I mentioned there, they were implemented like in 2010 or 2012, and the last bug fix was in 2015 maybe, but they still somehow work, and they're still feature complete. So yeah, it's hard to believe. So this is serial port audio, and this is bindings to port audio library, and basically it's the same library that is used by Python. So p-audio is the most widely used library out there, and they also just bindings to this library. And what you do, you can open audio stream, and then you just read it and do something. Right, so this is one approach. If you want to record the microphone, then the other way is again the library that was written by some cool guy, Rob Blackwell, that allows you to read a WAV file, and unfortunately it does not allow to write it. So at least I had a read phase, and this was more than enough. And this diamond thing is serial arrows library that is a part of closure library of the same fashion, and it really allows you to avoid that much nesting with your braces, so you can have like a sequence of commands that you do. Okay, so I loaded some sound somehow, right? And now the question stands like, what did I load? Because it's also a tricky part, right? And it appears that I lost well, the wave, right? But how did I load it? Then I found out that okay, you have a frequency rate, right? And sample rate it should be, right? And this is just a series of measurements that you do, and then you just put it in the array. But of course, there is a trick, and the trick is that when you have more than one channel, right, and then you have your array is intertwined, so you have one sample from left, one sample from right, and so on and so forth. So if you don't know this, things can be strange to you. So yeah, it's good to know. Okay, so output, same stuff, serial port audio, and yeah, just works. So. After I loaded the sound, I decided that it would be nice if I can render it. So you see, I didn't even get to processing phase. It's just like I tried to do stuff. So first, my idea was like, okay, it's so simple, right? You create a window, you render graph, and that's it. You're done, right? So it's almost mission impossible with SBCL and graphic libraries that we have, because most of them are tied well. SBCL and macOS have some problems that they block bind thread to render the window, or if you do it in a separate thread, it doesn't work. So I don't know. But anyway, so after a week of doing the first thing, right, and I went to the stage with the star. Then suddenly I thought like, okay, but I have Emacs. Right. Like, why do you need anything else if you have Emacs, right? That's so simple. Yeah, and I had easy gnplot library that basically can generate a graph, right? So, of course, everything is possible with Emacs, and of course, it's possible to render image. And what you can do is first you allow Emacs to accept Common Lisp code, so that you can eval something from Common Lisp in your Emacs, right? And then there is a slide media add-on that allows you to basically render images. And it appeared to be all that you need to do the thing. Not really. This is a Common Lisp part, which is also very nice, I think. So when you do anything in the Common Lisp REPL, right? So it prints the output, and to print it, it calls print object method, and it's generic, so you can dispatch against it. So what I did, okay, so when I print object, if it's a path name, right? If it points to PNG file, then you just go and plot library, and you plot thing in Emacs. And that means that whenever I call the plot PNG library, I get the image back, and so the task was solved in this way. Very cool, I think.
But then you still have to generate the PNG, right?
Yeah, so this is a very sad story, because there is basically no good plotting library in Common Lisp. At least I did not find it. and most of them are just binding of some sorts to gnplot. So yeah, the one I chose maybe it's not the best one, because what they do is they generate a huge chunk of text, basically a gnplot program, and then they throw it into gnplot and then see what happens, and if we're lucky, then we'll get an image back. Yeah. So yeah, this is how it works. You basically print, and if you think about the wave, right? So we have a sample rate of 40K, and you have, like, for example, 10 seconds. So you have 400,000 dots, and then you try to render them, and then you feed all this text to the plot. So yeah, but still, it worked better than SDL that did not, right? So. And then I got to analysis part. Here I was almost devastated because I spent so much time on the previous part. I think I spent like 2 weeks trying to figure out just how to load things and to display. And then I just went searching on YouTube. Please help me, like sound processing. And fortunately, there was a talk by Anna Zhebrowska, processing music on the fly. With Python, unfortunately, but still. So it contained the part that I needed, basically analyzing the wave for spikes and register them. And her outcome is to play it back with notes. I didn't want it, so good enough. Here is a talk and here is a repo, so you can check it out. But basic algorithm is this. So all these squares. You had a string of blocks that you have, right? That you read from the file or from microphone. Then you do operation to calculate the spectrum. So this is block, this is block. Then you have a string of spectrums. Then you calculate the flux, which is a single number, right? And then this stream of numbers gets into the window. So there's a ring buffer, and where you get these numbers, and what you do with these numbers, well, you calculate the mean value. And if it's above some threshold, then hooray, you have a spike. So of course there are a couple of parameters that you can tune. It's a window size. You can have it of whatever size you want, and also a threshold. So this is it. So again, fortunately, it's a really funny story, because people complain a lot about plugging libraries in a Common Lisp world, but in my exploration, in every single aspect, there was a one library somewhere on GitHub, published 7 years ago, but doing the right thing. So, and it's just awesome. So again, I thought the code in Python state, you just do Fourier transform, you get the spectrum, you apply the Han window, you combine them, here you go, all is good. So I didn't know any of those, but I googled if there is a single library doing Fourier transform, doing Han window. So yeah, and basically, yeah, what it does, you get this buffer, you make a Fourier transform, then you plot some window, then you apply Han window on top. I think you multiply them, yeah, and then you square every single number in the buffer. And the flux is basically reduced when you subtract one spectrum with another, right? All frequencies, and then you sum up the result. So, and here I got to the interesting part, because I thought at this point I already lost the hope to solve original problem. So I thought that, okay, then we can just do something about sound processing, right? So I thought this is what I come up with, that we can invent the notion of so-called analyzers. And that means that something that sits at the end of this of the stream that you get from somewhere, right? And do analysis. And to turn anything into analyzer, we have a set of generics, which is setup processor, cleanup processor, and analyze buffer. Yeah. So, and here is how you start things. right? So in first case, the load wave will load actual file, right? So it will do some operation. But in this case, if we do, do something for load data from microphone, it will do nothing. It's basically not op, right? Because what we actually want to do, we want to get the data when we really need it, and we need it only on the processing step. So this is how you would. This is how it's possible to combine these analyzers. So in in the first case, you load the audio from the file, and then you apply two analyzers. And one of them is actually a player. So you set up a player, and then you output every buffer into the audio stream, and you can hear it, right? And the second one is actual analyzer that counts spikes. And you can apply the same stuff to the microphone. So you can say analyze wave with the same class. Yeah. And the neat thing is that with generics, since they are not tied to object, right? So you can basically turn anything into analyzer. So I had a class that I ported from the Common Lisp, or no, from the Python, right? That does analyzing the way it does. So I just implemented this analyze buffer generic from the previous step that did the thing, and the analyzer automatically made an instance of this class, and then, well, it just worked by himself like this with any input. Yeah, and this is an audio. So again, with the step processor, you just open the audio stream, and with the analyze buffer, you get the buffer, the array of numbers, right, and you throw them in the output. And when cleanup processor is called, you close the stream, and this is all this needed. And this is all. This is the whole analyze wave function that allows to compose them and to run them. So what it does is take all the instances, all the classes that you pass, that you want to have, right? So it runs setup processor on every single of them, and it's not necessary to implement this function because it's no op if there is no implementation, right? And then for each buffer, it's another magical function, right? So it's like for each buffer you do something. You run them one after another. And since the analyzer are mostly for side effects, right? You don't need to store any output from them. And in the end, you just clean everything up.
So for something like this, I think I would normally use an line protect. You know that?
Oh yeah.
Because you have to clean up probably, right? So.
Yeah. Well.
So if an error occurs, you're left in a mess.
Yeah.
But, yeah.
To be honest, my code never breaks, but.
Oh, I see. Sorry, didn't realize that.
Just joking. It's a crude prototype, and of course you need to wrap every single step there.
Yeah.
Yeah. So this magical for each buffer. What does it mean? So this is implementation of this for real-time wave, and this is the reason why it wasn't op when I just created the wave, right? Because when I just create it, I don't need to process anything. But when I do want to process anything, then I open audio input, and then I read the data from the microphone, and then I feed it to these processors that I had previously. And for them, it's very transparent because they just it's just a callback, and they just get a buffer with the numbers. Oh, bonus! Yeah, and for static wave, the one that I loaded from the file, it's also very simple because you already have all the data, right? And then you just loop over it and call the same callbacks. And again, it's transparent. It's abstracted from the actual analyzers, so they don't care actually where they get the data from. Okay, so it was magic. Now bonus. Yeah, the bonus part. I thought that we had discussion with Raphael about what to do with this stuff, and Raphael said like, okay, like filters sound awesome as well. So I thought like, okay, challenge, and now we have filters. So what's it about filters? So you have a wave of sorts, so that you load it from somewhere, from the microphone or from the file, and then you apply. I didn't write, but these brown things are filters, right? You just stack them one after another, and every single one of them works like this. It again takes input, throws output, and then you pipe it out to another one. So I thought that it would be interesting that once you apply a set of filters, right, what you get on the output is just another wave, right? So you can take it and then again apply another filter, and then you will have another wave. So you can have a series of objects that you can do something with it. For example, you can plot every single object after you apply a couple of effects or things like this, right? Or you can do it in the very end. And yeah, here we go. It's the same stuff. The difference is that now we have the parent wave slot. And why I did this? Because I thought that it would be fun to do some lazy evaluation. Because for example, when you just apply effect, right? You maybe don't want to output it right away. And if you don't want to output it right away, then well, why would you process it, right? So, and another thing to take into consideration is that it's very useful, again, from our discussion with Raphael, that whatever filter you have, it works on the stream, right? And it should output the buffer of the same size that was the input. So we should not hold the values, and that allows to compose them very nicely, because you always have the input and output. Yeah, and since it's just a wave in the output as the one that we loaded from the file, then we can just plot it as the usual one that we loaded from the file. Yeah, so then the question is, where do you actually implement the effects, right? And since we have this magical for each buffer function, this is the only place in the whole file where we do actually need to get the data. So once someone called it, we just specialize this function against the filter wave class that I showed you, and then you basically do the same stuff as you did with the analyze wave, right? You stop all the filters, then you run them in a loop, and also you don't just accumulate data and send it, right? You apply all the filters and then call a callback, so that it can stream the filtered value down the road. So and the callback can be your analyzer that outputs stuff. In this sense, you don't need to hold a huge chunk of data anywhere. You just stream it to the output, and then you again clean up. And the other method that requires materialization of data is audio data, which is a method that used to load, to get the whole array of numbers. Right? Obviously, this method does not work for real-time data. Right? You cannot get all sounds in the world. But for static wave or for things like this, it works, and you might want to have it. And there could be a lot of cool tricks there. For example, you can cache the wave, right? So once you materialize data, you just store it, and then you don't run the same stuff again. I decided not to go with this because in this case you can change your effects on the fly, just recompile them, and then run processing again, and all your sound will go down the same pipeline, but with the changed data. Yeah. So to do. This is everything that can be done. It's like you can not just process data in real time, right? You can record the sound and then interact and then play with it in the REPL. So apply filters and things like this. saving sound would be awesome, because yeah, if you filter, if you manipulate the sound, and then you don't have a way to store it, it's yeah, it could be sad. Or multi-channel processing, because I operate only with one channel, or mixing the waves, so that you have one wave, you have another one, and you apply effects like noise or delay or whatever you find necessary, and then you might want to combine them again. So things like this. Yeah, or slice, so that you take only the first second of your file to so that you can iterate faster. And the other sad thing is the proper metric operations. What I mean by this is that whenever I implemented like multiplication of array by a number, for example, I was really jealous at Python guys, because in this world with an NumPy, you just multiply one thing with another, and you get the array, and you get the array multiplication. So everything, yeah. And I did not find a good library in Common Lisp for this. And so credits. These are all the libraries. They work. They rock. And CLSlice is basically a library that allows to slice an array. It's hard to underestimate, but it's very useful. So I think this is the end. It appeared that with a Common Lisp with surprisingly small amount of code, you can go very far. But of course, it's hard to beat the Python ecosystem with all the niceties that they have and all the well, loads of the documentation. Anyway, so returning to this one. Did I manage to count the jumps? Till the time when I actually did the stuff, right? So I managed to find the rhythm that I don't need to, that it's not hard anymore, right? So, no, I do not count the jumps. But it was interesting. Demo time and questions. Oh.
You want to see your jump?
Hmm?
You want to see your jump?
So, I think the sound itself won't be. Yeah, it's hard to hear, and also I have to do a confession that I screw up the wave loading, so it loads too slow, and the record for sound is too fast from the microphone is too fast. So, but that happens, right? So, yeah. For example, plot test amplification. We can do this one, and I hope I'll get enough screen for this. So basically what it does, yeah, so plot test amplification function. What it does, it loads the wave from the file, right? Then I just cut it manually because I did not implement the slicing part, right? So I decided like, okay, hotfix, and then we apply the amplifier filter that basically multiplies every number in the buffer by a number, right? And then you pass it to plot wave, and the ratio should be an argument. Let's see if it works. Let's say 3. Please. Demos should work.
It briefly flashed.
Oh yeah.
Yeah.
Okay. 0.3. You see, well, the plot is too big to fit into the into the screen. Okay, let's multiply it by something like 30. Should flash again. So as you saw, yeah, the numbers are much higher. Yeah, okay. So you see the wave increased the amplitude. So it kind of works. Yeah, analyze data from mic. Oh.
If you multiply it by half, you already have something to lower the volume as well. So this
yeah,
2 in 1.
Yeah, we can do this as well. Yeah, you see it. So now the amplitude is smaller, but the shape is the same. Yeah, I won't jump, but I can place. Yeah, I'm not a true Emacs user. I use evil mode, so yeah. Let's see. You see, when I bang on the keyboard, it somewhat detects things. Not always, not very reliable. So yeah, here we go, and this is the end. Oh. Yeah. Questions?
That's a quick question. From where you did get the inspiration of building the whole analysis this way? I can recognize Web API, Web Audio API. Obviously.
I don't know. To be honest, I just thought that it makes sense.
Just exactly the way they did it, with small exception.
Yeah. So maybe I wrote the manual, then forgot about it, and then I thought it's my idea. But to be honest, I did not read anything specifically. But I thought that. So the whole process makes sense, right? So when you do an analyzer, you don't want you want it to be abstract away from the output or from the input. So you just want to plug it somewhere and it works. So and then if it works on the string, you want to set it up or tear it down, because you might want to save some data, right? For example, you have a window, a white window, and you want to store data about it, right? You need to set up things and to finish them. No question.
When you define filters, is it in time space or in frequency space? Or both? Like before or after you do the Fourier transform?
Filters.
Before.
It's not about Fourier transform though.
Okay.
Yeah, so it's up to you to do whatever you want in your filter. So you just you get the buffer and then you're free to do something with it. So my analyzer gets the buffer and then it does everything in the callback, Fourier transform and stuff like this. But it's not required, so you just get this raw area and you do whatever you want. Okay.
It's not really a question, but it's more like this reminded me a bit. It's slightly related with live coding. This stuff.
That would be cool.
It's really cool that you do. That they do. They have some sound synthesis packages, and then they just code live, and then you can see it in the screen. Then they make music with a REPL or a Scratch.
I saw this stream about graphic engines. There's on Lisp Reddit some guys that develop stuff. Yeah,
it's really cool because then you can, like for example, get a scale and say just play random notes within this scale. It's really interesting.
That's a very good point about the live coding, because with Emacs and Common Lisp you get this for free. So you load the wave, and then you have a code, and then you can apply one to another, and you're not restricted to any GUI or something like this, right? So if you want to paint this, you can do this, and if you want to convert it back, you can do this, and it's very cool.
Yeah, there's sort of an organization or community called TopLab. Maybe the website is toplab.org or something, that is from people that do live coding. And there they have a bunch of resources and links to software, like environments that people use to do this. So I think it's a good thing to follow, like if people are interested in the concept. I think I remember one person that did this, that actually did it in Common Lisp with some library that hooks into that with Super Collider. It's pretty cool.
So like, what is it? Is it live coding or live?
Live coding.
So what is it a concept, or what is live coding?
So for example, you have this for the you have some software synthesis library or program running another process, and you're interacting with the interpreter or with your REPL, and you're actually writing code live in front of an audience. It's usually projected on the screen, and you're evaluating your commands to the synthesis server or library and making music on the fly with your code.
So it's like music related.
But
Yeah.
not
graphics
necessarily.
No.
Yeah, there's graphics as well. There's events that they call algo raves, like algorithm raves. So there's actually parties with the format. It's pretty. There's like a scene. I guess.
Is there raining in the area?
Sorry?
Is there raining in the area?
I don't know.
Tonight maybe.
Let's wait a bit. I assume there are.
That's awesome.
So the question would be, was it a pleasure for you to play with this task like in Common Lisp, or you just, it's not the language that I...
I think the most frustrating part is a library one. So when you don't have a good library to do matrix operations, right? It's really.
You just write it.
Hmm?
You just write it, right?
Yeah, maybe, but there is a bunch of people in Quick Lisp with their libraries, and they wrote it, and then they're gone. So it could be another one, right? With a competing abandoned library. But anyway, I think the main pro is the interactivity, so that you can actually take the sound and just do analysis or like actually see that the thing works in real time, not just by running a script and looking at the output.
There's a library in Common Lisp called Common Lisp Music. I don't remember exactly when it started, but it's already pretty old. That is for synthesis in Common Lisp. There's also one called Nyquist, but it's not Common Lisp, it's just Lisp, and it's tied into Audacity, the audio editor. So these are two sort of Lisp synthesis environments that sort of easy to get started with these things. For people that want to try this.
Okay, thank you.
Thank you.